Ladies and gentlemen, welcome back. I have to switch to English. I'm sorry, and I think also the mic is not working, so it wasn't a problem that I started in Dutch. But I said I'm very happy to see you back here because yesterday I came to my hotel and I was really happy about the day of yesterday. I had a wonderful day. I don't know how it was with you, but I was really inspired by the speakers. We had a lot of people talking to one another. We had the people from the private companies. We had the people from the organizations, from the government. We have the scientists. We have the people who are just working every day in our safety region, the fire department, and all the private companies advising our companies, our civilians, about everything that has to do with safety, fire safety engineering, with our incident management. So altogether, for me, it was a wonderful day. So I hope you also were inspired and had a good day yesterday. So I'm just looking if you agree with me, but yeah, okay. Thank you. So for all the people, are there people who are here for the first time today who weren't here yesterday? Oh, some of you were here not yesterday. Well, we are very happy to meet you here and that you're here. Very welcome. My name is Jolanda Trijslaar. I'm the chief of the fire department in Rotterdam, and I'm also a chairman of the Risk Management Council for the fire departments in the Netherlands. And I will advise you to sign in for 2 days tomorrow, next year, because it's really a wonderful congress where we connect science and operational knowledge from people who are working in the field and people who are doing research. This 11th National Fire Safety Congress, Science Congress, sorry, is organized by the Fire Service Academy, and I have to look at my paper, the Foundation of the Fellow FSE, from the University of Eindhoven. And they are also the two parties who will do the first part of this morning, because we have a very exciting thing we start with. We have interesting speakers for today, but we also have an award to give away. So it's really exciting for three students who wrote a thesis, and they are selected already. So they're going to give a presentation first, and after the break we have 3 very wonderful speakers again, and in the afternoon we have the workshops. So first I want to introduce to you my esteemed colleague from the safety region Noord-Brabant, Paul Verlaan. Paul is a very intelligent fire chief. He is schooled academically, which is very special in our field, I think. I think you're one of the only one who did some research as a scientist, and he is also a firefighter till the end. So I'm very happy that he's here, and he is the chairman of the jury of this award committee. So Paul, can you please come and introduce us to the 3 nominees? And I think I have to give the mic to Paul also. No, he's okay. Well, yeah. Paul, the floor is yours, and okay. I wish you all a very nice day. Oh, I forgot something. Sorry, Paul. I always wanted to be a flight attendant, and I had to tell you that in case of the unlikely event of an emergency, we have 4 doors to get out of this room. Don't follow the leader, don't follow me, just follow the people from the institute. They are recognizable by a jacket. You can keep your high heels on as a lady, so that's very good. There's no life jacket underneath of your chair. And what else do we have to say? You can take your stuff.
The gestures.
Oh yeah, the to the left and to the right. So yeah, so I think I said everything I had to say, and also you can send, of course, tweets, especially when we just have a winner in an hour.
Yes.
So then it would be very nice if you can send out a tweet.
Okay.
Well, thank you.
Yeah,
Paul.
Thank you, Jolanda, for your nice words. I'm becoming a bit shy by that, but welcome at the Fire Service Academy and Organization of Fire Safety Consultants Thesis Award. I'd like to announce 3 presentations by 3 excellent students, of course. And but first I'd like to mention that these 3 nominees, the 3 students, were selected by the Organization of Fire Safety Consultants. And I also will take the opportunity now to inform you that this organization will organize a conference on pool fire focus on December the 6th. That will be held in Leusden. So please fix that in your agenda. We have a dense program, so I will try to continue this session now, and I will introduce to you the first speaker, and that is Melchior. So Melchior, the floor is yours. You have 10 minutes.
Okay, good morning everyone. So I have the honor of kicking off the second day of the FSS Congress. And I'll do that by introducing to you or giving you a crash course in multiscale modeling, more specifically multiscale modeling of fire and accelerator tunnels, and even more specifically fire and accelerator tunnels at CERN. But first, who am I? Melchior Schepers, and this thesis research was, this is not working. Yeah, wait, one back, okay. Let's see. Okay, let's try again. So this thesis research was performed in the framework of the International Master of Science in Fire Safety Engineering. It's a framework between 3 universities, so the University of Ghent in Belgium, the University of Edinburgh in Scotland, and the University of Lund in Sweden. I myself did this research at the University of Lund in Sweden. It was also a cooperation with CERN at the border of France and Swiss. Currently I work at FESG in Belgium, so that's where their logo is on there as well. So what was the goal? Well, the goal was to investigate the feasibility of multiscale modeling of fires in the underground particle accelerators being used at CERN, and more specifically by using FDS, so the Fire Dynamics Simulator. Now this might all seem quite abstract, but don't worry, I'll run you through it, and then hopefully by the end of the presentation you know more or less what I'm talking about. We'll look at multiscale modeling, we'll look at what is CERN actually, then from that we'll build a reference case, we'll subject that reference case to some sensitivity studies, and then finally some conclusions and suggestions for future work. Okay, so what is multiscale modeling? Well, if you listened yesterday to Bart Mercier, he told you that CFD, or computational fluid dynamics, is a very computationally costly operation to perform. So what we want to do in multiscale modeling is you want to split the domain. You want to split the domain in a really detailed 3D part surrounding the fire, and then a much less computationally costly 1D part further away from the fire. So you can see it over here. You have a really long 3D part. Let's say, for example, you want to model a fire in a tunnel, and spoiler alert, they have a lot of tunnels at CERN. So you're basically going to split in a really detailed 3D part around the fire, and then 1D further away from the fire. You can model the 3D domain then using CFD, be it either Reynolds average Navier-Stokes or large eddy simulation, as is done in FDS. And then the 1D domain, you can solve it using much more computationally efficient methods, such as network modeling based on graph theory. Now, the most important thing in a multiscale model is how long do you want your 3D domain to be? So you really want to determine where to place your interface between the 1D and the 3D domain. You can do that by looking at a metric called the Froude number. This is the Froude number as defined by Ingeson. And it basically tells you where the flow becomes fully developed. What do I mean by fully developed flow? In the beginning, your smoke will be stratified. Then the further away you go from your fire, it'll start mixing, the smokes will start to mix with the ambient air, and then finally your fire will become fully developed. You have smoke everywhere, and basically you don't have any gradients anymore in the cross-section of your tunnel. So you only have a gradient in the properties of the smoke along the longitudinal way of the tunnel. Which I mean by that is that, for example, temperature and velocity will be constant over the height of the tunnel over here, so that if you model this part in 1D, basically you won't lose any information anymore. How is that made available in FDS? In FDS it's done by using the HVAC module. It's not really intended for multiscale modeling of tunnels. So it has some limitations. More specifically, there's no mass storage, or it's not well supported in the 1D domain. There's also no heat transfer in the 1D ducts, and that's a major, well, perhaps a flaw even. And also there's a really big absence of the fan control possibilities. So for example, if you want to regulate your ventilation speed inside the tunnel, the control possibilities are quite limited in FGS. Okay, so hopefully this more or less made clear what multiscale modeling is. Now I've been talking about CERN a lot. What is it? Well, it's Conseil Européen pour la Recherche Nucléaire, so basically the European Organization for Nuclear Research. It's located at the Franco-Swiss border near Geneva. And they have this huge tunnel underground, 27 kilometers long, a circular collider. And they accelerate protons in there. This is what it looks like. So 27 kilometers long tunnel, about 100 meters underground. And it's really complex inside. You have these technical caverns, you have other technical rooms. It's really long straight sections. You have then bands in it as well. But if you simplify it a bit, you can come up with something like this, which already looks a lot simpler, luckily. And then this is how their ventilation system works. So they insert air through one shaft. The air flows to that side and to that side, and it's extracted at the two neighboring shafts. The depiction you see here consists of 8 3-kilometer long sections. Now I'm fully aware of the fact that 8 times 3 is not 27 kilometers long, but anyway, it's a simplification. In reality, you have to remember that it's much more complex. Okay, so that's CERN and multiscale modeling. From that simplified model I just showed you, I then built a reference case which was 640 meters long for the 3D domain, which you see over here. Placed a fire in there, 1 megawatt fire, alpha T squared, as almost everybody does. The simulation time was taken to be 800 seconds. The vertical ducts were 100 meters long, and the longitudinal velocity inside the tunnel is 0.6 meters per second, or the equivalent of 5 cubic meters per second, which is extracted at every second or every moment. So you see the 3D domain over here, and then the neighboring 1D domains over there. Computationally, I tried a coarse mesh, a medium mesh, and a fine mesh. You can see them over here. So the coarse one was 50 centimeters by 40 by 50. The medium one was 20 by 20 by 20, and then the fine one was 20 by 10 centimeters by 10 centimeters. Now, just to give you an idea about the computational time needed, for the coarse mesh, it was 14.24 core hours. For the medium one, 340, let's say, and for the fine one, about 3,000. Now, a core hour, if you have a PC at home with 1 core, it would take about 3,000 hours to run the simulation. Luckily, I was able to use the HPC facilities at CERN, and then this one runs at about 20 hours. Okay, so then that reference case was subjected to a bunch of sensitivity studies. I extended the 1D domain. So what happens if you put extra 1D sections beside your 3D domain? What if you want to model the entire tunnel by extending it with 1D domains? What happens if you increase the flow rate? What happens if you change the interface position? So what happens if you make the 3D domain smaller? Your simulation will run faster, obviously, because your 3D domain is smaller, but do you lose accuracy? And then finally, as well, sensitivity to the wall lining material inside the tunnel was also checked. I'll now just jump to the conclusions. So what I saw was that extending the 1D domain without including extra 3D domains really didn't change that much. The system is also much less sensitive than I expected to change in the 3D domain, so I was able to make the 3D domain much smaller than the 640 meters and still come up with more or less the same results. Which means that at this point, the Frade-Ingesson, which I introduced to you, is not really a decent indicator of the needed 3D domain length. So it's a sufficient indicator, but it's conservative, so it's not a necessary condition. And finally, the main conclusion is probably that a lot more research is needed, and also a lot of validation of the results is necessary, as always with CFD, of course. I don't know if there's time for questions, or I'm allowed to answer questions, but Otherwise, just come to me and we'll have a chat.
Yeah. Melchior, yeah. Melchior, thank you for your nice presentation. Unfortunately, there is no time for questions. I can imagine that you like to pose questions, and there is an opportunity because in the surroundings somewhere here, you have a poster. Yeah. So if you would like to pose questions to Melchior, there is an opportunity during the break or afterwards. So please do so. I will continue immediately, and Nick, I will give the floor to you.
Okay, thank you. Hello everyone, my name is Nick ten Bult and I graduated in June of this year from the University of Eindhoven. And the title of my graduation project was Cooling of a Hot Smoke Layer by a Sprinkler Spray, validation of a CFD model. And I did this project in collaboration with POETS, so all the experiments I did at their facilities. The main objective of the study was to gain experimental results to validate a CFD model and to gain insights in the cooling effects of the sprinkler spray. So now I will explain something about the experimental setup we used. It consists of two cabinets. The first one is the burner cabinet. Here we have a small fuel tank with a heptane pool fire, and when it's ignited, the smoke starts flowing into this larger cabinet where a smoke layer is formed, and then a part of the smoke is extracted by a mechanical fan, and in the exhaust duct we analyze the smoke, and we measure the oxygen and carbon dioxide concentrations. We use this to determine the heat release rate of the fire, which is later used in the simulations. Within this smoke cabinet, there's in the middle, there's one sprinkler nozzle. It's a relatively small nozzle with a K factor of 80 liters per minute square root bar, and it's activated manually, so we could create some consistency between the experiments. And as you can see here, maybe there are there's an array of thermocouples, and we measure the temperature within the smoke cabinet to get information about the temperature of the smoke layer. Then the CFD model. It was also done with FDS, the Fire Dynamic Simulator from NIST. And this is a large eddy simulation model. And this means that the large eddies that are larger than one grid cell are numerically solved, and the eddies that are smaller, they're modeled with a turbulence model. And I used a uniform grid of cubic cells from 5 centimeters, and this resulted in a total amount of cells of a little over 620,000. And as Melchior just explained, I tried to make it also more efficient, and that's why it's divided in 6 subgrids. As mentioned before, the heat release rate that was put into the model came from the measurements. Also, the exhaust volume we measured was put into the model. And to model the sprinkler spray, I had to be a little bit creative, which I will explain now. So when a nozzle is activated, the water jet hits the deflector plate of the nozzle, and the water starts waving, and eventually these waves break up into lines, and the lines breaks up into small droplets. However, this process of creating droplets is too complex to model in FDS. So the atomization process had to be inserted in the model in a different way, and therefore a spherical coordinate system is used. This means there is a sphere around the nozzle at which the particles are injected, and as you can see, you can divide this sphere into smaller pieces, and each piece you can give a different mass fraction of the total water volume and different velocity, so you can create a less uniform water distribution. And to get input for the model, I performed a bucket test. So I was measuring at the ground floor in different directions and at different distances the amount of water that was sprayed onto the floor. And I calculated back the trajectories of the droplets. And this was used to create an input table with for all these small surfaces with a different mass fraction. And I compared those results with the tests I did, and there was quite a good agreement. And if you're interested in this, I have some nice pictures of that on my poster. Then the results. You see a movie of the one of the experiments, and at the first line, the sprinkler is activated. So that's now. And you see that the black line, the bottom line, is the temperature, the average temperature that was measured. And the blue line over here is what the temperature would be if the sprinkler was not activated. And as you can see, it would still be increasing, and this was due to the fact that the heat release rate of the fire wasn't as constant as I wanted. And what you see here is that there's approximate difference of 70 degrees within the temperature, and now the sprinkler nozzle is deactivated, and what you see is that the temperature gets back up. So this is a nice indication that the thermocouples stay dry. I use some small shields to prevent them from wetting and measuring the water temperature. Now, if we compare this with the model, in the first part of the simulation, the model follows the measurements results quite good, but then after a while there's already an overshoot, and this is before the sprinkler activates. So at the moment of activation, the sprinkler is the temperature is already overestimated. And there are two lines. The blue line is a model without sprinkler, so you can compare that to the previous slide with the top line, the dashed line, and the pink line is a model with the sprinkler activation. As you can see here, the cooling between those two lines is much less than was measured, and here the cooling is around 40 degrees Celsius compared to the 70 degrees in the measurements. And here we have the results of another experiment with a slightly lower water flow rate. So what you see is in the first 90 seconds there's quite a good similarity between the model and the experiments. Then after a while the model starts over-predicting the temperature of the smoke layer, and then at activation it's already a little bit over-predicted. And then in the model there is a much faster response time, and what you see after it reaches its minimum, it starts to follow the line of the model without sprinkler, and it has a really has a constant amount of cooling during the activation time. And again, the cooling is under-predicted in the model here, where we have here a cooling of around 26 degrees, and if I'm correct, in the experiments it was around 50. The conclusions, what we saw in the experiments, we had a smoke layer between 150 and 180 degrees Celsius, and this was reduced between 50 and 90 degrees for the different water flow rates. If we compare that to the model, in the FDS, the initial smoke layer temperature, so before activation, is already over-predicted, and the cooling is under-predicted, so it's a little bit conservative. So smoke logging, I didn't really point it out in my presentation before, but with a higher flow rate, with smaller droplets, more smoke is dragged down. But in general, the main part of the smoke layer remains stable, and was in the top of the cabinet. Now, what if we want to apply this in practice? You need a relative fine grit, and maybe even a more fine grit to get more accurate results. And this also means an increase of computational time. The simulation took around 24 hours to run, and it was only for around 300 seconds. So you can imagine if you want to simulate a much longer time, you need a lot more time. And I think time is money, and often we don't have that. And also you need a very broad knowledge of the sprinkler spray pattern. So the buckets test I did are very intensive to do, and what you would want is maybe some information by sprinkler manufacturers, which you can use, but you really have to know what you're doing and how to apply it. So you have to really know what you're doing. So this was my presentation. Thank you for your attention, and yeah, feel free to ask questions.
Thank you, Nick, for your interesting presentation. And also in this case, if you would like to address questions to Nick, that's possible in one of the rooms. You also have a poster, have you? Yes, okay. The next presentation will be held by Kevin. So Kevin, may I invite you to present your thesis?
Well, good morning, everybody. My name is Kevin Smeyers. I work as a fire risk engineer at FPC Risk, an Antwerp-based company. I graduated this year at the University of Ghent in the postgraduate program in February. And I'm here, just like my colleagues, to tell you a bit about my thesis. What I did is I made a comparison of the European standard for the design of smoke and heat evacuation systems by the means of CFD modeling using FDS, like almost everybody does. Why did I choose this? Because it was my belief that the European standard is quite conservative. It is based on the BR368 calculation method, which in turn is based on empirical formulas and live setups and testing. So there are some, how do you say, constants chosen rather arbitrarily, and there are some constants just empirically determined, which might not be correctly interpreted in reality. Those of you who know and work with the norm know that it's a very complex calculation method. So what I tried to do in this is I tried to reproduce the same values using the CFD analysis, and even in a second step try to prove that there is a constant oversizing of the system. This would mean that we could reduce the design systems by maybe 10 or 15%, which would lead to smaller and cheaper installations, which is, of course, always the goal. So what I did is I created a standard fire scenario. I used a geometry, pretty simple one, just like the one presented here. You all know this image, I suppose. Then I put in a design fire based on the European code. It's a 3 megawatt sprinklered office fire, which we often use in designs. And we placed it on the ground floor because that would generate the highest smoke flow through the atrium. I also made some changes in the geometry. Some small changes, namely the presence of a downstand there or the presence of a balcony there. Why did I choose those? Because those are two parameters arbitrarily chosen, to my feel, which have a large impact on the mass flow rate we will actually measure at the top of the building, at the ceiling height or at the bottom of the smoke reservoir. Namely a downstand. If there is a downstand present, we would have to multiply the outflow of the mass out of the fire room by 2, which has a large influence. And the presence of a balcony will determine whether you have a free-flowing plume or an adhered plume, for which we would have different entrainment factors. So what I did is I measured the mass flow rate at the ceiling height. And then in the CFD model, I put in the exact same geometry, the exact same fire, and I tried to meet the European standards criteria. How did I do this? By making it an adiabatic building. So there's no heat exchange with the walls and the construction. And also I limited the fire curve, or I changed the fire curve, so that it would reach its maximum potential almost immediately to reduce the calculation factors, time, sorry. And this would give you faster steady state or equilibrium situations. And then I had a large opening at the ceiling through which all the smoke could flow freely outside. I put in a measuring device which calculated or which measured the total outflow. Results, they were quite surprising. Namely, the first two models, indeed we see that the SEN or BRE method is a bit conservative, 5 to 10%. And I'd like to point out that those are the models with the balcony present. We also see that the difference between the first and the second is the presence of a downstand, and the effect is almost, well, it's almost zero. Then again, the shocking result was in the third and fourth model, without a balcony present. The European standard is not only not conservative, but it's insufficient. Well, that's what the results show. Up to 42% for adhered plumes, which was quite a surprise. Now, what can we conclude from this? First of all, the BRE is not simply conservative. I think it's safe to say that we cannot assume that. What we saw is when the smoke flow leaves the fire room, it shoots out of the room at a high velocity and it enters the center. Wow. Have you heard a word I said so far? So, yeah, well, I guess I don't need this. So when the smoke actually enters the atrium, it shoots out at high velocity, which would leave, or in both cases, sorry. So with or without a balcony, the flow would reach the center of the atrium, and it would initially start out with a free-flowing plume. And only when there is no balcony present, it would actually be inclined to go towards the atrium wall and form a so-called adhered plume. Now, we also saw in the drawings, or in the images, that the adhered plume is not completely adhered, as in it's not half a plume, it's more 2/3 or 3/4. So we could assume that the alpha, the entrainment coefficient of 0.077, is not enough. There is more entrainment than is calculated within the manual calculations. That is one thing. The second thing is we need to be very careful when we're designing anything to check the validity regions. Within the manual calculations, I found that the temperature within the fire room is well below flashover conditions, so we could actually use the calculations. While the CFD analysis showed that the temperature rises well above flashover conditions, which would actually mean that we cannot use the European standard for this particular situation. I also wanted to point out that these results are for this specific scenario. If geometry would be different, if the design fire would be different, the results would be completely different, and maybe they would be more inclined to correspond with the manual calculations. What else do we have? I do believe that when an engineer designs this, and this may be the most important conclusion of all, when an engineer designs a smoke and heat control system, always check the validity regions and always check if your results are realistic. I think that's the most important thing we can say here, and never trust any of both methods blindly. But I do believe that further modeling can help define the right parameters and to help redefine the constants used in the manual calculations. But I also think it is very necessary to have more testing, live testing, to help develop new modeling tools. After all, it would help us all out a lot. Thank you very much. That was it.
Thank you, Kevin. You also have a poster in one of these rooms, so if you... The poster with no name on it, so if you have questions, address it to Kevin afterwards or during the break. So now we will come to the award itself, and I have to... speakers. And this will be, for our international guests, a bit confusing, because the jury report is in Dutch. So I will switch over to Dutch now, and happily the 3 nominees are all Dutch speaking, so that will be no problem. And you can be sure if I will translate it instantaneously, I will sure that I will lose some nuances, so I will not do that. Oké. De scriptieprijs, ingesteld door het Instituut Fysieke Veiligheid en de Vereniging van Brandveiligheidsadviseurs, dan horen jullie het ook een keer in het Nederlands. Die is voor de meest innovatieve en spraakmakende, relevante of fundamentele master of bachelor thesis. En dat moet gaan over brandveiligheid. Nou, die scriptie die moet zijn ter afronding van een master of bachelor opleiding in 2017 of 2018. Aan een onderwijsinstelling in het Nederlandse taalgebied. Dus dat rechtvaardigt ook een klein beetje dat ik het nu in het Nederlands doe. De scriptieprijs is een bedrag van €1200. Dat wordt straks ook uitgereikt en aan een Fire Safety and Science gerelateerd onderwerp. Misschien goed om nog even te noemen hoe het in het voorgaande jaren ging. In 2012 was het Rob Smeets die gewonnen heeft met de opkomsttijden bij woningbranden. 2013 Brecht de Brouweren, A Study of Initial Fire Behavior in Lower Energy Houses, Universiteit van Gent, de vorige was de TU Delft. In 2014 Thijs Geertsema, van trappen op de rem naar fluitend richting de inzet, van Saxion Hogescholen. In 2015 was het Sander, en dan moet ik het even goed uitspreken, Giunta Dalbani. Fire Behavioral Sandwich Panel Core Materials in de Pre-Flashover Phase. Dat was van de Technische Universiteit Eindhoven. In 2016 Jelme Veestra, en dat is een hele ingewikkelde titel, FDS2 Abacus, a Two-Way CFD FAM Coupling, van de Technische Universiteit Eindhoven. En in 2017 Cindy Veerman, rookgasexplosie, ook van de Saxion Hogeschool. De jury, we hebben het bekeken, de jury die bestond uit Ruud van Herpen. Waar zit je, Ruud? Ja. Ricardo Wever en mijzelf. En Liewe de Witte, zit ook hier, ja, was de secretaris. Goed, de genomineerden, nou die heeft u allemaal kunnen zien en kunnen horen. En ja, dan denk ik dat het goed is om nog even te noemen dat de VVBA scriptiecommissie, die heeft in samenwerking met de TU Eindhoven op 13 september jongstleden tijdens de expertclass FSA Next Generation op de TU Eindhoven de 3 genomineerde scripties bekendgemaakt. En die zijn geselecteerd uit allemaal inzendingen van voornamelijk technische scripties. De algemene indruk van de nominatie was dat naast alle bovengenoemde aspecten met name beoordeeld is op het innovatieve karakter van de scriptie, de spraakmakendheid, maar ook de relevantie van het onderwerp en de resultaten en de mate van toepasbaarheid voor de brandweer. De scripties zijn technisch over het algemeen van een vrij hoog wetenschappelijk niveau. In 2 onderzoeken ligt de focus op de modelmatige aanpak, dat heeft u net kunnen horen, zonder experimentele verificatie. En 1 onderzoek is gericht op de validatie van een model door middel van praktijkexperimenten. De uitkomsten leveren dan ook vooral een bijdrage aan de modelmatige theoretische benadering van de Fire Safety Engineering. En de resultaten zijn hiervoor vooral toepasbaar in het theoretische kader rondom brandveiligheid. En in beperktere mate dan in de praktijk. De scripties hebben interessante onderwerpen aangepakt en bevatten interessante constateringen, zo hebben we geconstateerd. De uitkomsten zijn zowel voor het werkveld als voor het vervolgonderzoek waardevol. Goed, laat ik dan even kort de nominees toelichten. Ik begin even met de scriptie van Kevin. Als wij een nadere beschouwing daarop zetten, dan zien we dat, of als ik even naar het oordeel van de jury kijk, dan zien we dat de jury van mening is dat het een gedetailleerd onderzoek is naar de vergelijking tussen 2 verschillende methoden om rookverspreiding te berekenen voor een stationair brandscenario. Het onderwerp is gedegen, hebben we geconstateerd, en een voorbeeld voor de vergelijking van verschillende methoden. Echter, de conclusies zijn niet baanbrekend en er mist experimentele verificatie, waardoor de praktische toepasbaarheid ontbreekt. De jury beoordeelt de actualiteit en de layout van de scriptie als meest positieve punten. En daarentegen wordt de jury de innovatie en de toepasbaarheid als minder sterke punten van de scriptie. Tot zover de scriptie van jou, Kevin. Dan de scriptie van Melchior Schepers. De jury is van mening dat het onderzoek naar het beperken van de rekentijd in CFD voor de lange CERN Accelerator Tunnel met een brandscenario interessant is en van een hoog wetenschappelijk niveau. De jury mist wel de praktische validatie van de data, waardoor de praktische toepasbaarheid wordt verkleind. En het onderzoek is volgens de jury zeer innovatief op het gebied van fire safety engineering. De jury beoordeelt ook de wetenschappelijke onderbouwing en mate van innovatie als de meest positieve punten van deze thesis. En daarentegen beoordeelt de jury de relevantie en de mate van toepasbaarheid als minder sterke punten van de scriptie. Nick. De jury is van mening dat dit onderzoek naar de invloed van sprinkler op de rooklaag boven in een brandruimte zeer interessant en wetenschappelijk goed onderbouwd is. Het onderwerp is actueel in de fire safety engineering en levert interessante resultaten op. Het resultaat is nog niet direct toepasbaar, maar de combinatie van modellering en experimenteel onderzoek in deze scriptie is een goede stap in de richting van de toepasbaarheid. De jury beoordeelt de leesbaarheid, probleemstelling, doelstelling, aanpak en de actualiteit als meest positieve punten. Daarentegen beoordeelt de jury de mate van toepasbaarheid als minder sterk punt van deze scriptie. Ja, en dan komen we nu natuurlijk toe, want ja, één van jullie is de winnaar. En dan één zullen we de scriptie award ook uitreiken. En ik kan jullie zeggen dat de jury heeft de scriptie Cooling of a Hot Smoke Layer bij Sprinkler Spray van Nick ten Bult van de Technische Universiteit Eindhoven uitgeroepen tot winnaar van de IFV-VVBA scriptieprijs 2018 en kent hem ook de prijs van €1200 toe. Goed. Nick, mag ik je even naar voren roepen, want dan moeten we ook overgaan tot de feitelijke overhandiging daarvan. Die moet zelfs nog even ondertekend worden. Mag ik jij even op het podium... Kijk, het is zo actueel dat het zelfs nu nog ondertekend moet worden. Dit is hem. Goed, dan gaan we even voor het fotomoment gaan we hier staan. Als jij even... Nick, van harte gefeliciteerd nogmaals met deze award. Dank je wel. Goed, dat was dan uiteindelijk het moment van de uitreiking van de award. Ik dank overigens alle nominees voor hun presentatie. En wens ik ook heel veel succes toe in hun verdere loopbaan.
Sorry Paul, blijf even staan als je wil. Want ik wil graag even van deze gelegenheid gebruik maken om even wat te zeggen. I will turn this into English so everybody can understand. Paul, I think it's your last time. Is that true?
Yes. Yeah. Last time for what?
Yeah, that's a good question. We did this thesis award for the 7th time, and Paul has been for 7 years our chair.
Yes.
And actually, January 1, you're going with retirement.
Yes, yes.
So, and actually, the last time for this award, I made it really difficult for you.
Yeah.
Because I sent you the report in Dutch, and then told you 1 minute before you have to do it in English.
Yeah.
So that's a big mistake by my side. But I really want to thank you for 7 years being our chair. You do this really, really good. And even if I say to you 1 minute before, you have to do something else, you will try to do it. So, Paul, give him a big applause. And thank you.
Thank you.
Well, ladies and gentlemen, I forgot to tell you that we have a lot of international people here, but of course the international people themselves, they know, but we have really people from all over the world. We have people from Finland, Sweden, Denmark, Germany, Belgium, the UK, the US, Canada. Yesterday I saw people from Portugal and the Dutch Antilles. And of course, the Netherlands, not to forget the Netherlands, because we're very happy that you're also here. So I'm glad that Lua said, sorry to the international people that you couldn't hear the whole explanation about the jury. But I think it was wonderful to have the 3 presentations in English, and all 3 of you, congratulations. But just being here, to give your presentation for this international audience, I think that was really fantastic. And it is also one of the goals of this Congress to connect science with our working field and the people who are working with it daily. And I also heard there is still a challenge that we can connect science with our practice a little bit better, but maybe you're still young, so maybe that will be a good challenge for you for the future. But congratulations anyway, especially for the winner. Ladies and gentlemen, we're a little bit ahead of schedule, so that's very good, because after the break we need more time. So you will have a short break till 11:15, so don't look at the program. 11:15 you have to be back here, because then we have the speakers of this morning, and they have a very interesting presentations, both theoretical and both from practice. So they will be very interesting. So now enjoy your break, enjoy the coffee break, and please be back at 11:15. Thank you.